All right, welcome ladies and gentlemen. This is the video on heating curves and how to do calculations from a heating curve, and essentially talking for the first time about phase changes and IMFs. So in this we're going to be looking at the heating curves and cooling curves that you remember from Regents chemistry, and talking about how we can actually take some of our thermochemistry information like Q equals MC delta T and apply it to a heating curve. Now before we do that though, it is very important to understand what's happening with intermolecular forces when we undergo phase changes, because heating curves are about a substance undergoing a phase change. We have that period on the heating curve where something is melting, where something is vaporizing or boiling. So if phase changes simply involve either the formation or the breaking of IMFs. Melting and boiling, so where we go from a solid to a liquid or a liquid to a gas, we are breaking intermolecular forces of attraction. And this should make sense, right? Because a liquid has more freedom of motion than a solid, so therefore it cannot have as many IMFs as a solid does. A gas has significantly more freedom of motion than a liquid. The particles are not actually touching in a gas, so naturally we have broken the IMFs that are holding the liquid together in order to turn the liquid into a gas. But this process of breaking intermolecular forces of attraction is requires heat. And the point is also that when we do this, we are not actually turning the molecule into something else, right? If you melt water, you still have water. So no chemical bonds are broken, right? That's a big point. When we're undergoing phase changes, we're not breaking chemical bonds. And in the opposite direction, condensing or freezing. So when we turn a gas into a liquid or a liquid into a solid, now we're talking about bringing our particles closer together, right? The gas particles have to move closer together, and they have to form IMFs in order to turn into a liquid. The boiling point and the melting point both are direct comments on intermolecular force of attraction strength, right? And we've seen this before. A high boiling point indicates that we have very, very strong intermolecular forces of attraction. So the next slide that I'm going to show you is a short video from the textbook. It's really quick, and it just talks about the heating curve, cooling curve, and the phase changes that are happening there.
As energy is added to a solid can be summarized by a heating curve. This section of the graph represents water in the solid state, or ice. Starting at a low temperature, we see that the temperature rises as energy is added. In this region, the added energy increases the motions of the solid molecules, but the molecular motion remains centered on a fixed position. This section of the graph represents the melting of ice to form liquid water. When the curve abruptly changes slope to zero, the solid is melting. Here, all the added energy is used to overcome the intermolecular forces holding the water molecules together in the solid structure, allowing the water molecules to move around more in the liquid state. There is no further change in temperature until all the solid is converted to liquid. This section of the graph represents water in the liquid state. Further addition of energy causes the water molecules to move around faster, increasing their kinetic energy. The water molecules are attracted to one another by hydrogen bonds, but the rigid structure characteristic of ice is no longer present. Water is more dense than ice because the structure is more mobile and the cavities present in ice are no longer maintained. This section of the graph represents the vaporization of water. In this area, the temperature remains constant again, in spite of the addition of energy. The added energy is used to overcome the intermolecular forces between the molecules in the liquid, changing the molecules into the gaseous state. The temperature remains constant until all the liquid evaporates. This section of the graph represents water in the gaseous state, or steam. Addition of energy raises the temperature because the kinetic energy of the molecules is being increased and the molecules are moving around more rapidly. The molecules in the gaseous state are far apart and relatively independent of one another.
Okay, so we have a fairly nice reminder of the different sections of a heating curve and what's happening in terms of phase changes at each of these sections. You've seen this in Regents before, but you still have to know this and you still have to understand this about a heating curve now. So we're going to look at this in detail with not just heating curves, but also something called phase diagrams, which I have a separate video on. So the phase of a substance, so whether a substance is a solid, liquid, or gas, is dependent on what temperature the substance is under, what pressure the substance is under, and the strengths of the IMFs that are in the substance. So with phase changes, we have names of all the phase changes here, along with some of the names that we need to make sure we acquaint ourselves with. Heat of fusion, heat of vaporization. So fusion, because it's been a little while since you might have heard this, reminder that this means, in this context, melting. We look at this definition, heat of fusion, the enthalpy change, so remember enthalpy, so we are talking about energy again, associated with melting a solid. So this is a constant, right? Heat of fusion is a constant. How much energy does it take to melt a solid? And it's usually measured in terms of kilojoules per mole or kilojoules per gram, or joules per mole or joules per gram. So how much energy is needed to melt 1 mole of the substance, or how much energy is needed to melt 1 gram of the substance. And you saw in Regents Chem, you might remember that you had the heat of fusion of water was 334 joules per gram. It was actually on your reference table, delta HF. And heat of vaporization, so now we're talking about boiling, right? That's another word for vaporization. How much energy is required to vaporize a liquid? And again, this is going to be in joules per mole or joules per gram. And you can have it in either. It is reported as either, because we know easily, hopefully, how to convert between the two. Now, looking at this figure on the right, we have all our various and sundry phase changes. Focus on the first half, because this really kind of gets divided in half. And if we look over here, we have phase changes going from a solid to a liquid, so melting, a liquid to a gas, so vaporizing, but then also, remember, we have sublimation, which is going directly from a solid to a gas, bypassing the liquid phase completely. It will not melt, it will sublime. And in this case, for all of these, IMFs are broken. Right, these are the guys where we're breaking intermolecular forces of attraction, like this we're talking about in the video, how when you melt something, all the energy is going into overcoming some of the intermolecular forces of attraction, how when you boil something, all the energy is going into overcoming IMFs. That means breaking. So IMFs are being broken on this side. Now if you're breaking IMFs, that requires energy. So all of these processes, all of them, are endothermic. All of them will have a positive delta H value. It takes energy to do this. Then looking at the other side, we have the opposite processes. So the opposite process of melting is freezing. The opposite process of boiling is condensation, going from a gas to a liquid. And the opposite of sublimation is this process called deposition. So that might be a new word for you. If it is, then consider that a new vocabulary term, deposition, going directly from a gas to a solid. So we say the gas is sort of depositing into the solid. Make sure you know that. You would be responsible for that. And in this case, in terms of all of these processes on the right, condensing, freezing, deposition, we are forming intermolecular forces of attraction. We are bringing our particles closer together, and they are setting up their IMFs. So in this case, because we're forming intermolecular forces of attraction, that will make the substances more stable. A liquid is more stable than a gas. A solid is more stable than a liquid. So these are actually exothermic processes. Which is what I'm talking about on this next slide here. Heating curves, they're graphs of temperature versus heat. Temperature versus the amount of heat added, also possibly time. That's one thing that is frequently seen on heating curves. It could be time as well. And again, we have this segmentation of our phase changes. All the phase changes that involve breaking IMFs are endothermic. All the phase changes that involve forming IMFs are exothermic. And the ones that involve breaking intermolecular forces of attraction, so this is going to be solid to liquid to gas, these are on a heating curve. meaning you're heating something up, you're adding energy in, that's why it's endothermic. All those that involve forming IMFs, so gas to liquid to solid, this would be our cooling curve. The substance is losing energy. And yes, I am saying here that freezing is an exothermic process. Because, if you think about it, because you're like, well, that doesn't make sense because freezing is cold. Freezing is a liquid losing energy so that it can become a solid. The liquid has too much energy and it must release it. It must get rid of it. It has to in order to become a solid. So freezing is actually an exothermic process. Now, our two constants, heat of fusion and heat of vaporization. How much energy is needed to melt a solid? How much energy is needed to boil a liquid? Heat of fusion is typically less for all substances than their heat of vaporization. The heat of fusion for water is 334 joules per gram. The heat of vaporization for water is 2,260 joules per gram. So almost, 7 times larger. And that's because when you move from a solid to a liquid, which we have in fusion, we are not overcoming all of the intermolecular forces of attraction. You're only breaking some of them, right? A liquid still maintains most of the IMFs of a solid. Yes, we have broken some. Yes, there's definitely more freedom of motion in the liquid, but a lot of them are still there. Versus in vaporization, a liquid to a gas, you are completely separating all of the molecules from one another. So you are breaking all of the IMFs, which is going to take a lot more energy. So it always takes more energy to boil something than to melt it. All right, so heating curves. Hopefully this should look pretty familiar to you. We've got the different sections of the curve, which the video talked about a little bit. We have the first section where we have just a solid, right, in here, and that's it. That's all we have. And then we have the melting point temperature. Again, we have temperature on the y-axis. And we notice that the temperature stays constant when it melts right here. Right, so this is melting, so this is our solid going into a liquid. And it says solid and liquid in equilibrium. That means that you have both phases, both solid and liquid when something's melted. They're present together. Then after it melts, we see the temperature increase again. Right, this is where it's just a liquid, but temp is going up. So all the heat that's being added is simply increasing the average kinetic energy of the liquid. Once we get to the boiling point temperature, then we have our phase change. So the liquid and the vapor are now present in equilibrium. That means that you have both of them there. But again, the temperature is not changing, and whatever temperature that happens at, that is the boiling point. And then the last portion, we have the where we have just the gas, just the vapor, and all the heat that's being added is going into increasing the average kinetic energy of the particles. This is a heating curve, so all of these processes are endothermic. All of them, and we are breaking IMFs at all of these phase changes. Now, I have to erase some of this because I need to continue writing on this later. In terms of thermochemistry and heat calculations, each section of a heating curve is actually related to a calculation for heat that we can do. We can use the formula Q equals mc delta T for any part of the heating curve where temperature is changing. So where we are increasing the temperature of the solid, where we're increasing the temperature of the liquid, where we're increasing the temperature of the gas, we can use Q equals mc delta T. We can know the mass of the thing, know the specific heat of the thing, know the change in temperature of the thing, and you can actually figure out how much heat is needed to do that. You can calculate that. But you cannot use Q equals mc delta T for the parts of the curve where the temperature is not changing, i.e. the phase changes. You have to use a different formula. So in that case, we're going to use Q equals MHF, this is mass, or Q equals NHF, this is moles, when we're undergoing the melting phase change. So knowing whether to use mass or moles, it will basically depend on the HF. Is HF in joules per gram, or is it in joules per mole? And whatever it is, then that's what you use. But you cannot use Q equals mc delta T for the entire thing, because then you won't be taking into account when the temperature is not changing, but energy is still being added. And likewise, we're going to use Q equals mHV or Q equals NHV when we're undergoing the boiling phase change, when we're turning the liquid into the solid. And in order to find the total amount of energy that happened in the process, all you have to do is add all your Q values together, and then that's it. So to go back and look at this again, if I wanted to figure out how much energy it takes to get from the start to the end, I'm going to simply break this up into the different line segments and do a Q calculation for each one. At this first one, I'm going to do Q equals MC delta T because the temperature is changing. At this second one, because this is melting, I'm going to do Q equals MHF or NHF. At the next line segment, from B to C, I'm going to do Q equals MC delta T because temperature is changing. At CD, because temperature is not changing, but heat is being added, I can't just do Q equals MC delta T for the whole thing. I'm going to do Q equals MHV or Q equals NHV. And for the last one, where temperature is changing again, I'm just going to do Q equals MC delta T. And all I need to do to figure out how much energy is needed, again, to get from the very beginning to the very end, is simply add together all of those Q values. And that's it. And that's what we're going to go through on this problem right here. The only thing that I'll add in addition to that is that you have to be very careful with specific heat, because the specific heat of a solid is not the same as the specific heat of a liquid, which is not the same as the specific heat of a gas. So for water, for example, the 4.18 joules per gram degree Celsius, that's just the specific heat of liquid water. It's not the specific heat of gaseous water, which is what we have in this problem. So the question says, how much energy is required to raise the temperature of a 10-gram ice cube from -5 degrees Celsius to 75 degrees Celsius? And then we have a whole heck of a lot of constants. We have the heat of fusion of water, the heat of vaporization of water, and then specific heats of ice, water, and steam. Again, showing you that we have different numbers for specific heats for the different phases of matter. The first thing that we want to do in this problem is recognize that we're talking about water, which means that we know that the normal boiling point, and we can't assume unless we're told otherwise that we are under 1 atmosphere of pressure. The normal boiling point of water is 100 degrees Celsius, and the freezing point, or melting point, is 0 degrees Celsius. So we are starting below the freezing point, and we're ending somewhere between the freezing point and the melting point. So what I recommend you do is actually draw a little heating curve for the water based on the temperatures that we're starting at. So we're starting at -5 degrees Celsius, right? We know that. And we're heating up this ice cube. But it's not just going to go straight from -5 to 75. It's going to go from -5 to 0. And then the temperature is going to stay the same for a while because it's going to melt at 0 degrees Celsius. And then it's going to go up and it's going to end at 75 degrees Celsius. As I said, you want to figure out how much heat is needed. You break each of the line segments down, do a calculation for each of them, and then simply add them together. So we have 3 line segments here: A, B, B, C, and CD. Each of them gets a calculation. From A to B, the temperature is changing, so we're going to use Q equals MC delta T. From C to D, the temperature is changing, so we're going to use Q equals MC delta T. From B to C, however, the temperature is not changing, so it's melting, so we're going to use Q equals N HF. Now I know that we're going to be using Q equals NHF, meaning joules per mole, because I look at the values that we have. Right? We have that one right there. We have joules per mole, so I know we're not using Q equals MHF. And that's all we're going to do. That's all I'm going to do right here. That's all we have to do to solve this problem are these 3 Q values, and then simply add them together. So the first one, AB, Q equals MC delta T. The mass of the water is 10 grams. There it is, the problem. 10 grams. Now, specific heat. At this point, we have ice. So we need to use the specific heat of water when it is a solid, which is 2.09 joules per gram Kelvin. That's a big thing. Make sure you don't use the wrong value for specific heat. And yes, I am substituting out degrees Celsius here because this is based on changes in temperature, and a 10-degree change in Kelvin is the same as a 10-degree change in Celsius because of how the conversion works. And then we have to multiply it by the change in temperature. Well, between A and B, the change in temperature is 5 degrees Celsius. Right, so again, grams cancel, look at that, degrees Celsius cancels. And when you do that math, 10 times 2.09 times 5, which make sure you do to make sure that you get the same value that I do, I get, I'm going to write it up here, 104.5 joules. Okay, so that's AB. Great, done. Next up, BC, which we said is going to be the Q equals NHF. Okay. Well, N stands for moles, and HF is the heat of fusion of water, which is the 6.01 kilojoules per mole. But again, we have per mole. I don't have moles of water right now. I have grams. So we have to do a quick conversion using water's molar mass to turn grams of water into moles of water so that units match. Units have to match. Always, always be on the lookout for that. So doing that math, I get 0.556 moles of water, and you multiply that by the specific, by the heat of fusion of water, 6.01 kilojoules per mole, and that will give you the Q value for line segment BC, which again, hopefully you should do as well, and so that you figure out that your numbers actually agree with mine. And I get a value of 3.339 kilojoules. Those of you who are paying attention might already be spotting a possible problem coming up. All right, and last one is CD, which is just Q equals MC delta T, but for a different segment. So this is the liquid segment, so now we are going to use the 4.18 joules per gram degree Kelvin. So mass of the water, again, is 10 grams. Specific heat of the liquid is not the same as the specific heat of the solid. And the delta T for this segment, 75 to 0, so 75 degrees Celsius. So simply doing that math out, multiplying 10 times 4.18 times 75, I get 3,135 joules. All we have to do to answer the problem, to say how much energy is needed to do this, to go from A to D on our curve, is simply add these numbers together. But I can't add them together as is, as hopefully you might have seen, because we have joules for the first one, we have kilojoules for the second one, we have joules for the last one. So you have to convert one of them. It doesn't matter which one you convert, as long as you convert one of them. I tend to like to go to kilojoules. You're probably going to tell me you'd rather go to joules. Sure, doesn't matter. But remember, there are 1,000 joules in a kilojoule. So I would have 104.5 joules from the first one, so this is AB, plus the second one converted to joules is 3,339 joules, so this is BC, plus, and then the last one, 3,135 joules, so this is CD. Simply add these suckers together, we get the answer to the problem, 6,757. And there we go. That's how we do calculations with a heating curve. It's a positive value because these are all endothermic processes. If it was a cooling curve, you should get a negative value because your changes in temperature will be going in the opposite direction.